Welcome students. In this class we will be learning the concept of derivatives of antiderivatives using Leadness Rule, and foremost we would have to know the formula for Leibniz Rule. So the formula is stated as follows: if f is continuous, then we are d over dx of integral g of x to h of x f of t times dt is equal to f of h of x times h dash of x negative f of g of x times g dash of x. So this is the all important formula we will be using in this chapter. So now what we will do is we will do questions related to this particular topic. Students, let's do this question. We've been given that g of x is equal to integral 2 to x squared with dt being in the numerator over 1 positive root of t. With x being greater than 0, we are expected to find g dash of 9. Now g of x is given, so let us just consider that. Consider g of x, which is 2 to x squared dt over 1 positive root of t. Now you might be wondering, how is it that we have resolved to use Leibniz rule? Now the catch is, observe the limits. One of the limits is a numerical quantity, the other one is a variable. The moment you come across such a situation, directly you can conclude that Leibniz rule is the way to go. So having mentioned that, let me just write that rule. We know that from Leibniz rule we got f of h of x times h dash of x negative f of g of x times g dash of x, which is equal to d over dx of integral g of x to h of x f of t times dt, right? Now we are asked to find g dash of 9. So this implies g dash of x is equal to d over dx of integral 2 to x squared dt over 1 positive root of t. This is what is expected to be sought after. So from here, what I wish to do is, clearly you can see that we need to take the upper limit. So let us consider now this quantity. Now this quantity is nothing but the function of g, right? So we will have to obtain, in this case we will have to substitute the upper limit. So g of x squared is equal to 1 over 1 positive root of x squared. This is one value, and then we have to find out the differential of this quantity. So differentiation of this has to be obtained, which we can actually take this as, let me just take this as, let h of x be equal to x squared, and this is going to be g of h of x. Therefore g of h of x is this, and h dash of x is equal to 2 times x. So this is one side. Now the other side is the lower limit. So in this case it's going to be g of 2. Now g of 2 is equal to 1 over 1 positive root 2, and g dash, that is going to be equal to 0. So if I were to take g of x is equal to 2, so this is nothing but g of x. right, which is nothing but 1 over 1 positive root 2, and g dash of x, g of x is equal to 2, so g dash of x is going to be equal to 0. So hence we can write that g dash of x is equal to, I'm stating it, g of h of x times h dash of x negative g of x times g dash of x. This is equal to h of x is taken to be as x squared times differential of x squared, h dash of x is going to be 2 times x negative g of x. G of x is 2, so g of x is 1 over 1 positive root 2. I should have placed that value also here, but anyway I have just placed the value here. So let me just continue on. G dash of x is equal to 0, so this is going to go off. All that is left is g of x squared times 2x. But what is g of x squared? G of x squared is equal to 1 over 1 positive root of x squared times 2x. This is what we have got. But we have to obtain g dash of 9. This is what is required, right? So, but g dash of 9 has to be obtained. This means the value of x is equal to 9. So therefore g dash of x squared, so if I were to substitute in place of x, I need to substitute 9, so it's going to be 1 over 1 positive root of 9 squared times 2 times 9. This is equal to 1 over 1 positive root of 9 squared is positive, that means I'm taking the modulus, so 2 times 9 is 18, so this is equal to 18 over 9 positive 1 is 10, 2 divides 18, 9 times 2 divides 10, 5, so 9 over 5. So therefore g dash of 9 is 9 over 5. So this is the right place for us to draw the red line. Of course I have been a little bit in detail. I have done that for your understanding, right? Because it's highly necessary that we take the function for h of x, or take the value for h of x as well as for g of x, and then obtain the outcome, so that you will be in a better position to relate to the Leibniz formula. So having got that, so we will move on to do other questions. The only way that we can master these topics is through practicing more questions. So that's exactly what we're going to do. So let's move on. Students, let's do this question. We are expected to find d over dx of integral x squared to x to the power of 3 1 over log t times dt. Now I can apply the Leibniz rule straightforward. Now you have to see that the limits are not numerical in nature, but they are variable in nature. So that's also a clue that we need to go forward with the Leibniz rule. Also there is a d over dx that is being given. So Leibniz rule is the most appropriate technique for us to evaluate. So having mentioned that, let me directly apply the Leibniz rule. So first thing is that we know that, let me just state the Leibniz rule. We know the Leibniz rule. So what is the Leibniz rule states? D over dx of integral g of x to h of x f of t times dt is equal to f of h of x times h dash of x negative f of g of x times g dash of x. Now I can directly apply the Leibniz rule here. So this is equal to, in place of t we substitute the upper limit. So that's going to be 1 over log of x cubed times differentiation of x cubed, that's going to be 3 times x squared, followed by a negative sign, and in place of t it's going to be x squared, so it's going to be 1 over log x squared times differentiation of x squared is 2x. So this can be rewritten in this following fashion. So what I will do is I can take log x. In fact, I can apply the formula. Since log a raised to the power of b is equal to b times log a, I can rewrite this as 3 times x squared divided by 3 times log x negative 2 times x over 2 times log x. 2 can be cancelled, 3 can be cancelled, giving me x squared over log x negative x over log x, which is equal to x squared negative x divided by log x. This is a very simple question, and this is the right place for us to draw the red line. So having got that, we will move on to do other questions. Students, we've been given this question: if phi is equal to integral 1 over x to root of x sine of t squared times dt, then we expected to find what is phi dash of 1 equal to. Now let us state the Leibniz rule. We know that d over dx of integral g of x to h of x f of t dt is equal to f of h of x times h dash of x negative f of g of x times g dash of x. So therefore phi dash of x is equal to d over dx of integral 1 over x to root of x times sine of t squared times dt, which is equal to, in place of t I substitute root of x, so it's going to be sine of root of x raised to the power of 2 times differential of upper limit. So it's going to be, let me just do that over here. So if y is equal to root of x, this can be rewritten as x raised to the power of 1 over 2, and I want to find y dash, which is nothing but 1 over 2 times x raised to the power of 1 over 2 negative 1, which is nothing but 1 over 2 times x raised to the power of negative 1 over 2, which is nothing but 1 over 2 times, I can push this down, x raised to the power of 1 over 2 would be in the denominator, which is nothing but root of x, right? So this is going to be 1 over 2 times root of x negative f of g of x. That means sine of 1 over x raised to the power of 2, right? Because I've got the lower limit as 1 over x times differentiation of 1 over x. So let me just show that over here. If y is equal to 1 over x, this is nothing but x raised to the power of negative 1. Therefore y dash is negative 1 times x raised to the power of negative 1, which is negative 1 times x raised to the power of negative 2, which is negative 1 over x squared. So this is going to be negative 1 over x squared. So this is what I've got. So let me simplify this. So this is equal to, this is going to become sine root of x raised to the power of 2 is x divided by 2 times root of x, and we got negative, that's going to be positive. So this is sine of 1 over x squared, I can just place it like that, divided by 1 over x squared, right? I mean, it should be, we are actually product multiplying by 1 over x squared, so that means this is going to be divided by x squared, right? So this is what we've got. So now we are expected, this is phi dash of x, so we are expected to find phi dash when x is equal to 1. So phi dash of 1 is equal to, so substitute the value wherever you see x, you substitute 1. So this is going to be sine 1 divided by 2 times root of 1 positive sine of 1 over 1 divided by 1 square. So what is this equal to? This is equal to sine 1 over 2 times root 1 is 2 positive sine 1 divided by 1. So if I were to take the LCM as 2, this is going to be sine 1 positive 2 times sine 1. 2 added with 1 would give me 3 times sine 1 over 2. So this is a good place for us to draw the red line. So that's a solution for this question. It's a lovely question, students. We'll move on to the next one. I hope you are practicing these questions. Students, we are given this question. F of x is equal to integral sine x to cos x e raised to the power of negative t squared times dt, and we are asked to find f dash of pi over 4. Now we would be applying the Leibniz rule. So let me state that we know that d over dx of integral g of x to h of x of f of t times dt is equal to f of h of x times h dash of x negative f of g of x times g dash of x. So this is the Leibniz rule which we would be applying. So therefore f dash of x is equal to d over dx of integral sine x to cos x e raised to the power of negative t squared times dt, which is equal to, foremost what we will do, in place of t we would substitute the upper limit cos x. So this is going to be e raised to the power of negative cos x. So it's going to be cos squared x times h dash of x, differentiation of cos x. That's going to be negative sine x followed by a negative sign, and instead of t we will be substituting sine x. So it's going to be e raised to the power of negative sine squared x times differentiation of sine x. Differentiation of sine x would give me cos x. So if I were to rewrite this, this is going to be negative sine x times e raised to the power of negative cos squared x followed by negative cos x times e raised to the power of negative sine squared x. This is my f dash of x. Now we are expected to find when x is equal to pi over 4. So this will mean f dash of pi over 4 is required. So I'm going to substitute in place of x pi over 4. So it's going to be negative sine pi over 4 times e raised to the power of negative cos pi over 4. Let me just place it, cos pi over 4, but there is a square there. Place that, followed by a negative sign. I could have taken the negative sign out, but anyway, let's proceed. So it's going to be cos pi over 4 times e raised to the power of negative sine squared pi over 4. This is the value. Now we know that cos pi over 4 is 1 over root 2. Sine pi over 4 is 1 over root 2. So this would mean cos squared pi over 4 is 1 over 2, right? So this is negative 1 over root 2 times e raised to the power of negative 1 over 2 because of the square being there, followed by a negative sign, and this is going to be 1 over root 2 e raised to the power of negative 1 over 2. Now if I were to take the negative sign out, this is going to be negative 1 over root 2 of e raised to the power of negative 1 over 2 followed by positive e raised to the power of negative 1 over 2, right? But these two things can be added together. So this is going to give me 2 times e raised to the power of negative 1 over 2. There is a negative sign there. You place it there, divided by root 2. So this is what we have got. Now if you want, you can push this to the denominator. That would mean I get negative 2 over root of 2 times e raised to the power of 1 over 2. Again, if you want, depending upon the choices, suppose they might give this as a choice, or they might go one step forward and give this as a choice, right? So you got root 2 times e raised to the power of 1 over 2, and root 2 and root 2 can be cancelled, giving you negative root of 2 divided by e raised to the power of 1 over 2. So this is what we have got. Of course, when you say x raised to the power of 1 over 2, this means root of x, right? So you can clearly rewrite this as negative root of 2 divided by root of e, or you can rewrite this as negative root of 2 over e. So these are some of the deductions which we can expect in a multiple choice question. So one of these things are possible. So I have extrapolated all of these possibilities, and what is required from your side is to practice. So this is a lovely problem, and we have used the Leibniz rule here, right? So let's move on to the next question. Students, let us move on to do this question. We've been given that f of x to be equal to integral e raised to the power of 2x to e raised to the power of 3x t over ln t times dt, and x is greater than 0. We are expected to find the derivative of f of x with respect to ln x when x is equal to ln 2. So the most important noteworthy point here is we are expected to find f dash of x with respect to ln x. So that's critical. So what we will do is we will start off by applying the Leibniz rule. So let me state the Leibniz rule here. So d over dx of integral g of x to h of x f of t dt is equal to f of h of x times h dash of x negative f of g of x times g dash of x. So this is the Leibniz rule. So therefore let us find the d over dx of f of x. Now we know that, let me start like this, we know that, or given, you can either say given or we know that, given f of x is equal to integral e raised to the power of 2x to e raised to the power of 3x with the quantity inside being t over ln t dt. So therefore f dash of x, so what is f dash of x? F dash of x is nothing but d over dx of f of x, which is nothing but d over dx of integral e raised to the power of 2x to e raised to the power of 3x t over ln t dt, right? But applying Leibniz rule, this is going to be equal to, so applying Leibniz rule, we would now have, in place of t we would be substituting e raised to the power of 3x, right? So this is going to be e raised to the power of 3x divided by ln e raised to the power of 3x times differential of, or I should say differentiation of e raised to the power of 3x. So that's going to be e raised to the power of 3x. The coefficient of x is 3, so we place that there, right? And this has to be followed with substituting e raised to the power of 2x in place of t. So this is going to be e raised to the power of 2x divided by ln e raised to the power of 2x times differentiation of e raised to the power of 2x. That's going to be e raised to the power of 2x. The coefficient of x is 2. So that's the way we place the quantities. Now we know that ln a raised to the power of b is equal to b times ln a, right? So by that formula, this is equal to e raised to the power of 3x divided by, this is going to be 3x times ln e times 3 times e raised to the power of 3x negative e raised to the power of 2x divided by 2x times ln e times 2 times e raised to the power of 2x. This is what we have got. Now clearly what we can do here is cancel the 3's that we see here, cancel the 2 that we see here, and ln e, what is the value of ln e? Ln e is equal to 1. Ln e is equal to 1. So this is equal to, I've got e raised to the power of 3x times e raised to the power of 3x. So that's going to be e raised to the power of 3x raised to the power of 2 negative e raised to the power of 2x times e raised to the power of 2x. So it's going to be e raised to the power of 2x raised to the power of 2. So this is what we have got, right? Of course, ln e becomes equal to 1, but there is a presence of x, so we need to divide by x. So on the left hand side, this is what is the value for f dash of x. But we are expected to find the differentiation of the function with respect to ln x. So that is very critical. So if I were to rewrite this, let me just write this down. We are expected to find the differentiation of the function f of x with respect to ln x. This is what we are expected to do. Now what I'm going to do, I'm going to rewrite this as d of f of x divided by dx divided by d of ln x divided by dx. So dx can be cancelled, so we are not doing any changes here as such. Now this is rewritten as d over dx of f of x divided by d over dx of ln x, right? Now d over dx of f of x is nothing but f dash of x, and d over dx of ln x is 1 over x. But f dash of x is this quantity, right? So let's write that e raised to the power of 3x raised to the power of 2 negative e raised to the power of 2x raised to the power of 2 divided by x. Now this is divided by 1 over x. So if I were to flip it, clearly the x and x can be cancelled. So that would give me e raised to the power of 3x raised to the power of 2 negative e raised to the power of 2x raised to the power of 2. Okay, so now the question is not complete as yet. Now we are expected to find the outcome when x is equal to ln 2, right? So take this value, when x is equal to ln 2, we have to substitute the value over here. So this is equal to e raised to the power of 3 times of ln 2. This entire thing is raised to the power of 2 negative e raised to the power of 2 times of ln 2. This entire thing is raised to the power of 2. Now we know that a times ln b is equal to ln b raised to the power of a. This is the value we are obtained, or I should say we are given from the laws of logarithms. So this is equal to e raised to the power of ln 2 raised to the power of 3 raised to the power of 2 negative e raised to the power of ln 2 raised to the power of 2 raised to the power of 2. So this is equal to e raised to the power of ln 2 raised to the power of 3 is ln 8. This is raised to the power of 2 negative e raised to the power of ln 4 raised to the power of 2. Now e raised to the power of ln, so they get neutralized, giving me 8 squared. This also gets neutralized, giving me 4 squared. 8 squared is 64, 4 squared is 16. So we have to subtract 64 minus 16. So I get a 14 there, and this would be 8, and 5 take away 1 will give me 4, and the outcome is going to be 48, which is a good place for us to draw the red line. So that is the completion for this beautiful question. Students, I hope you enjoyed this. Of course, these are all rough work done for your understanding. So what we will do is, we will move on to the next question. This question is very interesting for the fact that we are expected to find the differential of the function with respect to a logarithmic quantity. And that is, in fact, when we see a question of that nature, most of the times there would be a light jitter because of the way the question is asked. But we have successfully achieved our final destination, so we will move on to the next one. Students, we are expected to evaluate the following question: limit x tending to 0 of integral 0 to x of 1 negative cos 2t times dt divided by integral. Of course, there is a x there. This is going to be 0 to x tan t dt. Now, since we are given a limit, we would have to apply the limit. So for us to apply the limit in the numerator, we would have to first integrate it. So this is rewritten as integral 0 to x dt negative integral 0 to x cos 2t times dt. I'm not doing anything with the denominator. Let me retain it as it is. So this is equal to integral of dt is going to be t, limits are 0 to x, negative integral of cos 2t is going to be sin 2t, coefficient of t is 2, the limits are 0 to x, divided by the denominator. I substitute the upper limit minus the lower limit, followed by I substitute the upper limit. I'm going to get sin 2x divided by 2, negative, I substitute the quantity 0, I'm going to get 0 everywhere. So this is divided by the denominator. Now if I were to rewrite this, this is going to be x negative of sin 2x divided by 2 divided by the denominator, which is nothing but x times integral 0 to x tan t dt. Now what is this exactly? The quantities that we have just obtained in the numerator. It is nothing but the application of the integral, and that has resulted as this value. Now we need to apply the limits, right? So let's do that. Applying limits, we get, so what is the limit? X is tending to 0. So if I were to apply the limits, this is going to be 0, negative sin 2 of 0 divided by 2 divided by 0 times integral 0 to x tan t dt. So this is not going to be of much importance to us because we got 0 here. So clearly the numerator is going to be 0, the denominator is 0, so 0 divided by 0 form. So this would mean we will have to apply L'Hopital rule, right? Differentiation of the numerator divided by differentiation of the denominator, right? This is L'Hopital rule. Now these differentiations are done exclusively. So this means d over dx of the numerator. What is there in the numerator? Integral 0 to x of 1 negative cos 2t times dt divided by differentiation of the denominator. I got d over dx of x times integral 0 to x tan t dt. Now once I got a derivative here and an integral inside, I'm going to apply Leadness rule. So by Leadness rule, what do we get? This is equal to, I substitute the upper limit in the function. So 1 negative cos 2x times differentiation of the upper limit 1 negative, I need to substitute the lower limit, so it's going to be 1 negative cos 2 times of 0 times the differentiation of 0 is going to be 0 divided by, it's u into v, so u times into differentiation of this quantity, right? So let me place a parenthesis. Differentiation of this quantity, I can apply Leibniz rule. So that's going to be tan, I substitute the upper limit, times differentiation of x is 1, negative, I substitute the lower limit, times differentiation of 0 is 0. So this is one quantity, right? U into v, differentiation of u now. So my v is this, 0 to x tan t dt, differentiation of x is going to be 1. So you don't have to specify it there, it's understood. Now this is equal to 1 negative cos 2x divided by x into tan x. This vanishes off, right? This vanishes, this vanishes. So what I'm left with, in fact this is going to be positive, right? So it's going to be d of u into v is equal to u times v dash positive v into u dash. So this is going to be positive integral 0 to x tan t dt. So now what I'm going to do is I'm going to apply the limits. Applying limits, we get. So what do we get if you have to apply x is equal to 0? This is going to be 1 negative cos of 2 times of 0 divided by. Now if you were to apply x equal to 0, this is going to go off. Now you got integral 0 to x tan t dt. So we need to apply the value x equal to 0 there. So if we were to apply the limits, this is going to be giving us 1. 1 negative 1 is going to be 0. This is going to be giving us 0. This is also will be giving us 0 as x is tending towards 0. So in fact we're getting 0 over 0 form. Now once we get 0 over 0 form, we need to apply L'Hopital rule again. Applying L'Hopital rule, we get. So let's do that. So differentiating the numerator, differentiation of cos 2x. Cos 2x is going to be negative sine 2x. We got a negative sign here, so that's going to be positive sine 2x. Coefficient of x is 2, so place the 2 divided by x times tan x. So it's going to be UVV formula. So x times differentiation of tan x is going to be secant squared x, positive. Tan x times differentiation of x is 1, positive. I need to differentiate this. So this is going to be tan x times differentiation of x is 1, negative tan of 0 times differentiation of 0. So that's going to be 0 there. So this is equal to 2 times sine 2x divided by x times secant squared x, positive tan x and tan x. This is going to be 2 times tan x. So we've got this quantity and we will simplify this. So what I'm going to do before I could apply the limits, I'm going to make the following changes. I'm going to divide sine 2x by 2 times x. In fact, the best way to say is I would dividing the numerator and the denominator by x. Now of course you have a 2 here, so what I would do, I would multiply the numerator of this particular quantity by 2. Of course there is also a 2 there, so let's place it. So in fact what I'm exactly doing here is I'm actually dividing the numerator and the denominator by x. That's exactly what I'm doing. Of course I wanted to have a 2 here because the fact limit theta tending to 0 of sine theta over theta is equal to 1. I want to apply this particular law or rule. You can say what you like. So that's the reason I'm placing this 2 and multiplying it by 2 there. Now this is going to be x times secant squared x divided by x, positive 2 times tan x over x. So this is what I've got. Now this entire thing has to have limit x tending to 0. So if I were to do that, so this would mean, or I should say, since limit x tending to 0 of sine 2x over 2x is equal to 1 and limit x tending to 0 of tan x divided by x is equal to 1, we will be using this property. Because of this property, I can clearly have this to be as 1. This is going to be 1. X and x can be cancelled, and as x tending to 0, secant squared x is 1. So this is going to be 2 times 2 is 4 of 1 divided by 1 positive. This is going to be 1. So I got a 2 times of 1. So this is equal to 4. 2 added with 1 will give me 3. So this would mean limit x tending to 0 of integral 0 to x of 1 negative cos 2t times dt divided by integral 0 to x tan t dt, of course there's an x here, is equal to 4 over 3. So that is a good place for us to draw the red line. So that's the solution for this question, and this is a beautiful problem which involves some application of the concepts that we have studied. So I hope you practice this, student, and as I mentioned to you, practice makes perfect. So with that, we will go on to the next question, and I hope you would enjoy the next question too. Students, we're given a beautiful question. Let me state that question here. Let f going from R to R be a continuous odd function which vanishes exactly at one point, and f of 1 is given to be equal to 1 over 2. Suppose that f of x, capital F of x, is equal to integral negative 1 to x f of t dt for every x contained in negative 1 comma 2, and g of x is equal to negative 1 to x t times f of t, and this is contained inside the modulus, times dt for every x element of negative 1 comma 2. If limit x tending to 1, capital F of x divided by g of x is equal to 1 over 14, then find the value of f of 1 over 2. Right? So this is what is expected from us, and the clue is f is given to be an odd function, and the point number 2 is we are given that limit extending to 1, capital F of x divided by g of x is equal to 1 over 14. So having got these things, let's do this question. Now I wish to write down these following informations. Right? So given capital F of x is equal to integral negative 1 to x f of t dt, right, and capital G of x is equal to integral negative 1 to x t times modulus f of t, right, modulus sine times dt. This is for g of x, this is for f of x, and we are given that limit extending to 1 of capital F of x over g of x is equal to 1 over 14. So now what I'm going to do is, let us consider limit extending to 1 of capital F of x divided by g of x. Now applying limits, what do we get? This is equal to f of 1 divided by g of 1. Now the question is, we want to know if it is 0 over 0 form. So now consider capital F of x is equal to negative 1 to x f of t times dt. Now at x is equal to 1, this is going to be f of 1 is equal to negative 1 to 1 f of t dt. Now it is given that f is a odd function. Since f is odd, this is going to be equal to 0, right, because of the fact that integral negative a to a f of x dx will be equal to 0 if the function is odd. We have already studied in the previous lecture. Also consider g of x be equal to negative 1 to xt times modulus f of t dt. Now this is modulus, so this is always going to be positive. So this is not going to be having any impact as far as the limits are concerned. So we don't have to consider this. So we just have a t here. And clearly at x is equal to 1, this is going to be g of 1 is equal to negative 1 to 1 t modulus f of t times dt. This is what we've got. Now this is negative 1 to 1. So clearly this is also going to be equal to 0. So this would mean applying limits, this is going to be 0 over 0 form. Right? So I did all this thing just to show you that f of 1 is going to be equal to 0 and g of 1 is going to be equal to 0. So once they are 0 by 0 form, we can now apply L'Hopital rule. Right? So what is the L'Hopital rule states? Differentiating the numerator divided by differentiation of the denominator. So we need to differentiate this. So this is equal to d over dx of f of x divided by d over dx of g of x. But what is f of x? F of x is nothing but this, minus 1 to x f of t dt divided by g of x is negative 1 to x. This is t times modulus of f of t times dt. So I will be applying Leibniz rule. If we were to apply Leibniz rule, this is going to be f of x times differentiation of x is 1 negative. I apply the lower limit and differential of constant is going to be 0. So there is no point in doing anything with that. And with this quantity, this is going to be x times f of x modulus sign, right? And we will have to, there are a few things we need to do in this case. So this has to be multiplied with the differential of x. So let me just place it like this. So that's going to be 1 minus, this is a constant here, so differentiating the constant will result in 0. So we don't have to worry about that. So this is equal to f of x divided by x times modulus f of x. This is what we have got, right? And what is on the left side? Well, the left side is actually, we started with the differentiation of the numerator of capital F of x divided by differentiation of g of x, right? So this is application of L'Hopital rule. Now it's time for us to apply the limits. So applying limits, this is going to be giving us f of 1 divided by 1 times f of 1, right? Let me just place the parenthesis. Okay, that's fine. Now what is exactly on the left side? If we were to apply the limits, okay, if we were to apply the limits, we would have to apply the value of x to the function also, because on the left side it is nothing but limit x tending to 1 of f of x divided by g of x, right? But this is given. What is that? Since limit x tending to 1 f of x divided by g of x is equal to 1 over 14, this is given. Hence we can equate this to be equal to 1 over 14. So this would imply f of 1 is already known, that's 1 over 2 divided by 1 multiplied with the modulus of f of 1, which is going to be 1 over 2, is equal to 1 over 14, right? This is what is required. So we can cross multiply this. So if we were to cross multiply, this is going to give me 14 over 2 is equal to modulus of f of 1 over 2 which is nothing but 2 divides 14 7 times, which means f of 1 over 2 is equal to 7. So that is the value, and it is a good place for us to draw the red line. So this is a beautiful question. Students, I hope you enjoyed this. So having mentioned this, what we will do is we will move on to the next question. Welcome students, we are going to start off this class by learning about Leibniz Rule, and it is rule number 1. Now the definition of Leibniz Rule, rule number 1, is given as follows: d over dt integral a to b f of x comma t dx is equal to a to b dou f over dou t times dx. So this is the Leibniz rule number 1. Now the most important point that we will have to note here is a, b are constants. Now I'm going to show you the proof for the Leibniz rule number 1. So let's do this. So foremost, what I wish to do is let us consider I of t to be equal to integral a to b f of x comma t times dx. So f is a function of two variables, x and t. Yes, you have heard it correctly. X and t are both our variables. And if we were to be given a function of this fashion, how are we going to integrate? So that is the biggest quest. It is imperative to understand that not all functions are integratable. Say for example, you are given integral 0 to 1 e raised to the power of x times dx. This can be integratable into an elementary function. So if I were to integrate this is going to be e raised to the power of x, right, within the limits 0 to 1. This is always possible. But if in case this is little bit changed, say for example, let me give you this illustration. Say for example, instead of this, if we were to be given say 0 to x e raised to the power of negative u squared times du, you cannot simplify this using elementary functions. It's just not possible. Of course, you can use the power series expansion for e raised to the power of x, or in this case it's e raised to the power of negative x square, u squared. But it is just not possible for us to simplify it via elementary functions. So that is why we need the help of Leibniz. So having mentioned that, let me just go on to show you the proof. So I'm considering this I of t to be equal to integral a to b f of x comma t times dx. Now let me differentiate this quantity. So differentiating this with respect to t, it's total differential. So d over dt of I, right? In this case it's I of t. Now if I were to apply the differential, or in other words the differential operator, to this function, then by definition I can rewrite this to be as limit delta x tending to 0 of I of t positive delta t negative I of t divided by delta t. Now where am I getting this? This is nothing but the popular definition of derivatives, where you would have seen such a explanation for differential, say limit h tending to 0 f of x positive h negative f of x divided by h, using the first principle where h is tending to 0, right? So we are exactly using this first principle and representing d over dt of I of t. Now I of t is integral a to b f of x comma t dx. So therefore what is I of t positive delta t? What is this? Let me write this down. We know that this is going to be equal to integral a to b f of x comma In place of t, I've got t positive delta t. So this is going to be t positive delta t times dx, and I of t is integral a to b f of x comma t times dx. So if I were to take this as 2, therefore I can rewrite 2 to be as limit delta x tending to 0. I'm going to place delta t like this. I of t positive delta t is integral a to b f of x comma t positive delta t times dx negative integral a to b I of t is f of x comma t times dx. This is what we've got. Now of course I can rewrite this further in this fashion. Limit delta x tending to 0 of, I can split this as integral a to b. I can club these two integrals in this fashion. F of x comma t positive delta t, this is one component, minus f of x comma t, this is the second component, divided by, I can push delta t inside, so this is what I've got. Now let me place this in square parenthesis and multiply it by dx. Now I want to push delta x tending to 0 inside, so this is equal to integral a to b limit delta x tending to 0 of f of x comma t positive delta t negative f of x comma t divided by delta t. Now this is placed inside the parenthesis with dx being outside. Now what is this? This is the explanation, or this is the exact meaning for a derivative, right, using limit concepts. So since I have two variables x and t, I cannot use total differential, so I will have to use partial differential. So since the given function is f, so it's going to be dou f over, the increment is occurring for t, so this has to be dou f over dou t, right, with the integral sign a to b and the operator dx. And what is this? This is exactly what we started with, right? This is the Leadness rule and hence proved. So this is a powerful concept, and we would apply this concept in solving complicated questions. Students, we are given a beautiful question. So the question is as follows: given g of x is equal to integral 1 to 2 cos t times x over t times dt, and we are asked to find g dash of pi. Now you might be thinking of integrating it and then finding the value when you differentiate the function and then subsequently substitute x is equal to pi. So that is not going to be an easy task because we got two variables x and t. So we need to apply Leibniz rule, rule number 1, because there is also rule number 2 which we would be also studying in a later lecture. So what I wish to do is I would be differentiating both sides. So if I were to differentiate this with reference to x, so it's going to be differentiating both sides with respect to x we get. So this is going to be d over dx, total derivative of g of x, is equal to d over dx integral 1 to 2 cos tx over t times dt. By Leibniz rule, if this d over dx goes inside, it becomes partial derivative. So this is equal to integral 1 to 2 dou over dou x of cos t times x divided by t, and you have dt there. Now in this case we have to differentiate x keeping t as constant. So that in turn would give us, let me write that down, this is equal to integral 1 to 2, when I differentiate cos tx is going to be negative sine t times x. Of course, you have to retain that t there, and the coefficient of x in this case is t, so place that t, and you have the dt there. I hope you are following me. So clearly what happens, you see, that's the beauty of this Leibniz rule. The t that is giving us complications is now being removed. So now what have we got? We have got, let me use this space over here. Right, so this is equal to integral 1 to 2, negative sign, I can place the negative sign out. And you have got sine t times x. And you have the operator dt there. So now we can integrate. Now this integration is done with respect to t, and x is kept as a constant. So we have no issue with that. So if I were to integrate sine t, there is going to be a presence of a negative sign. That negative sign will get neutralized by this negative sign. So coming back to the integral of sine t, we are going to get cos t times x. Now the coefficient of t is x, so I divide by x, and the limits are 1 to 2, so there is no change in the limits. So the limits have to be applied for t because the integration is done with reference to t. So if I were to apply the limits, this is going to give me cos 2 times x negative cos x divided by x, right? And what is this? This is my g dash of x. So this is my g dash of x. But we are expected to find g dash of pi. So when x is equal to pi, we are expected to find g dash of pi, which is nothing but, I substitute pi here, cos 2 pi minus cos pi divided by pi. Cos 2 pi is positive 1, cos pi is negative 1, so negative of negative will be positive, right? Divided by pi. So this is going to give me 2 over pi, right? And I can state that to be the answer, 2 over pi. So that is a good place for us to draw the red line. So this is a beautiful question, students. I hope you understood this question, and we will move on to the next question, though it looks a little bit challenging because of the presence of two variables, yet with the Leadness rule number 1 we were able to achieve the outcome. So we will move on to the next one. Students, we are given a beautiful question. We are expected to integrate integral 0 to infinity dx over x squared positive a squared raised to the power of 2. We have to get the outcome for this. Now this is x squared positive a squared raised to the power of 2. So it is imperative that we adopt some caution. Now what I wish to do is, I would like to use the following result. We already know that integral 0 to infinity dx over x squared positive a squared is equal to pi over 2a. We know this result. In fact, it's straightforward integration, and by that means we will be able to simplify this using elementary function, and subsequently upon substituting the limits we would get the value pi over 2a. That is the simple understanding. Now having got that understanding, let us go and use Leibniz rule. Only with Leibniz rule, in fact Leibniz rule is the shortest way by which we can simplify this and extract the solution for this question. So I'm going to state that by Leibniz rule number 1, we know that. So what do we know? We know that d over dt, its total derivative, integral a to b f of x comma t times dx is equal to integral d over dt is pushed inside, it becomes partial differential dou f over dou t times dx. Limits are a to b. So this is the important result you will have to keep in mind. So I would be using this result. So let me just take this as 2. So let us consider 2. So what is 2? 0 to infinity dx over x squared positive a squared is equal to pi over 2a. Now x is the variable, a is also the variable. That's the way I'm treating it. So what I wish to do is I would be differentiating both sides with reference to a. So differentiating both sides with respect to a, we get, so what do we get? This is going to be d over dA integral 0 to infinity dx over x squared positive a squared is equal to d over dA of pi over 2a. Now I push d over dA into or inside the integral, so that would be 0 to infinity dou over dou a of, I'm going to write this quantity in this fashion, 1 over x squared positive a squared times dx. So this is how I am representing the quantity. Now d over dA of pi over 2a. So let me just show you the working here. So this is d over dA of pi over 2a. Pi is a constant, 2 is a constant. So I can take pi out, I can take 2 out, so I get d over dA of 1 over a. Now I can rewrite this as pi over 2 d over dA. 1 over a I can take it to the numerator, so it's a raised to the power of negative 1. So this is pi over 2. I differentiate this, I get negative 1 times a raised to the power of negative 1, negative 1. This can be rewritten as pi over 2 negative 1 a raised to the power of negative 2, right? Which is nothing but negative pi over 2 times a squared. So this is what I get. So I can place that value here. Negative pi over 2 times a squared. So that's a nice value that we have got. So now we need to differentiate 1 over x squared positive a squared. So I would have to use, so let me use the space over here. So dou over dou a of 1 over x squared positive a squared. A is the quantity with which we are differentiating and x is constant. So this is going to be u over v formula. For those of you who would like to have a recollection, d of u over v is nothing but v times u dash minus u times v dash divided by v squared. So this is the formula we will be applying. So this is x squared positive a squared times differential of the numerator is 0 negative 1 time differential of this quantity. So differential of a squared is going to be 2 times a divided by x squared positive a squared raised to the power of 2. Now this is equal to negative 2 times a divided by x squared positive a squared raised to the power of 2. So this is what we've got. So let us club these two things together. So this goes here. So let me write that down. Negative 2 times a divided by x squared positive a squared raised to the power of 2, right? And I have a dx, don't forget that, and I have an integration sign. So the integration sign is 0 to infinity, and I got a negative pi over 2a squared. So all of these things are there. Now clearly what we can do is we can get rid of these two negatives there, and then we can push this to the right hand side, right? So if I were to do that, in fact I got a also, I can push everything to the right side. So this is going to be integral 0 to infinity dx over x squared positive a squared raised to the power of 2 is equal to pi over, I push this, I get 4 times a raised to the power of 3. Now what is this? What is this? This is exactly what was asked, right? And we have got the outcome. And this is a good place for us to draw the red line. And subsequently, to conclude, therefore, integral 0 to infinity dx over x squared positive a squared raised to the power of 2 has been found to be pi over 4a cubed. So that's a good place for us to stop, students. So this is Leadness Rule number 1. In the subsequent lecture, I would be dealing with Leibniz Rule number 2, which is a little bit advanced than this. So having mentioned that, I would like to request you all to review this, practice this, and then subsequently follow the step 1 and keep repeating until you get the mastery of this topic. Thank you very much. Have a good night.